So till now we have looked about the temperature distribution inside the infinite plane wall. Now we will see the thermal resistance of the infinite plane wall. So if we put this temperature profile in the Fourier law, we can get the heat transfer through the plane wall in watts. So writing like that, Q as minus Ka dt by dx, and we know that dt by dx, if we integrate it once, we get dt by dx as c1. So dt by dx is nothing but c1 value, and c1 value is, we know, is t2 minus t1 by L from here. Okay, so if we arrange it, heat transfer will come out to be T1 minus T2 divided by L by Ka. So it is like the temperature drop divided by thermal resistance. So always remember that thermal resistance of a plane wall will be L by Ka. L is the thickness through which heat is flowing. L is this thickness through heat is flowing like this in this plane wall, right? So this is for plane wall. There is an alternative way to find the heat transfer and temperature distribution. So it is by starting from the Fourier law. So what is that alternative way? Start from Fourier's law. Okay, and integrate it. Since Q is constant, through the plane wall, because there is no internal heat generation. So there is no internal heat generation, and there is steady state is maintained inside the plane wall. So whatever heat is coming from the surface 1 will cross the surface 2, and there is no change of the heat Q with respect to x. Okay, so we can take it out. So integrating from T1 to T2 on the right hand side, and from x equal to 0 to x is equal to L on the left hand side. Q can be taken out times L. By integrating we can get that, and K and A are constant with respect to temperature, so we can have T2 minus T1. Okay, so we can get the heat transfer as minus Ka by L T2 minus T1. Take this as equation 1. Again integrate this equation, but from x is equal to 0 to x cube integrate from x is equal to 0 to x is equal to x, and t is equal to t1 to t, means at any x temperature will be some t value, we don't know that. Okay, so we will get the expression like Q times x equal to minus Ka times t minus t1. Okay, so dividing these both equation, let's say this a and this b divided by a, we can have t minus t1 divided by t2 minus t1 divided by x by l. Same relation we got from the governing equation. Okay, and similarly if we put that, similarly from here we can get the thermal resistance value. Okay, q as t1 minus t2 divided by l by ka. Okay, and L by Ka is a plane area thermal resistance. Alright, so this was all about the steady state heat transfer for the plane wall case. Okay, now let's look for the second case, which is nothing but the infinite hollow cylinder. We have looked for the infinite plane wall, and now we will see the cylindrical body. Infinite hollow cylinder. Consider that there is an infinitely long cylinder. Infinitely long cylinder is its length is very larger than its diameter. Okay, and some fluid is flowing through it from the inside such that its inner wall temperature is maintained at T1 and outer, and it is kept in that some ambient, and because of that ambient its outer surface temperature is maintained at temperature T2. Okay, and we have to find the temperature distribution inside the solid material. So let me draw that. So this is the hollow cylinder I am talking about. Okay, so we want to find the temperature distribution, and let's say some fluid is flowing inside. Because of the temperature because of that fluid, hot fluid, let's say T1 is more than T2, and because of that some temperature drop is there inside the solid material of this hollow cylinder. We have to find the temperature distribution in this region. Okay, this is the length. So if we draw the cross-sectional view of that, we can draw like this. This is the inner part R1, this is the outer radius R2. Okay, this surface is maintained at temperature T1, this surface is maintained at temperature T2. Okay, and we have to find the temperature distribution, and as temperature is T1 is greater than temperature T2, so heat will flow radially outward. So we will start from Fourier's law. Q as minus Ka dt by dr. Why r? Because the cylindrical coordinate system is there in this case. So for cylindrical case, what will be the area? Minus k 2 pi r l times dt by dr. So in this case, again integrate like this, dr by r minus q minus k 2 pi l times dt. k, 2 pi, l all are constant, and integrate from r to r equal to r1 to r, and from t1 to t we will get ln of r by r1 minus k 2 pi l t minus t1. Okay, call it equation 1. Again integrate the above equation from r equal to r1 to r equal to r2, and t is equal to t1 to t is equal to t2. Okay, so what we are doing is, first we are integrating from t1 to some intermediate temperature which is a radius r. Okay, temperature t, and then we are integrating from t1 to t2, right? So if we integrate from these limits, we will get r2 by r1 minus k minus k 2 pi l t2 by t1. So dividing one equation and two equation, we will get t minus t1 divided by t2 minus t1, and on right hand side we can get r by r1 ln r2 by r1. So temperature distribution inside the hollow cylinder material is logarithmic variation. Okay, so this is t1, this is t2, r1, r2, and temperature distribution is logarithmic. Okay, so logarithmic temperature profile. Now if we rearrange the equation 2, we can get the heat transfer through the hollow cylinder. That what is this heat transfer value? So rearranging that, we can get T1 minus T2 divided by ln R2 by R1 divided by 2 pi KL. So similarly, this is like temperature drop divided by thermal resistance. So thermal resistance for hollow cylinder comes out to be ln R2 by R1 divided by 2 pi KL. For plain wall we have seen L by Ka, and for hollow cylinder it is ln R2 by R1 divided by 2 pi KL. Okay, so for next part we will see about the hollow sphere case.